Good morning. Myself, Dr. Shubhankar Sen, an associate professor in the Department of Mechanical Engineering, IIT ISM Dhanbad, welcome you to the fifth lecture of the first module of the 12-week SWAYAM NPTEL course, Finite Element Method in Thermal Engineering. In today's lecture, we shall elaborate upon the variational methods. We shall start with the Rayleigh-Ridge method. Then we shall discuss on the method of weighted residuals. We shall show examples from 4 fundamental method of weighted residual techniques, and eventually we shall close today's discussion by discussing the implementation of variational methods in formulating the finite element techniques. Now let us illustrate the Rayleigh-Ridge method with respect to one numerical problem. Consider a boundary value problem in one dimension. It is given as so d2t dx2 plus t equals to x over x equals to 0 to 1. So t is the degree of freedom, or t is the unknown, where t is a function of x, and the boundary conditions are both of essential type at the boundaries x equals to 0 and x equals to 1. So these are defined as t0 equals to 0 and t1 equals to 1. Let us take that also 0. So we have homogeneous essential boundary conditions. EBCs are both homogeneous. Now this is the strong form of the given boundary value problem. BVP is the boundary value problem. Now this is the domain. This is x. It is going from 0 to 1. This L, if you say it is 1, x equals to 0, x equals to 1, and here t equals to 0 and t equals to 1. Now to find the weak form from this strong form, let us start with the integral form of the governing equation. So the integral form of the governing equation is integral over omega, the weight function, into the strong form represented in terms of the approximate solution. So d2 th dx2 plus th minus x dx equals to 0. This is the weighted integral statement of the given strong form. Weighted integral statement of the given strong form. Here th, it represents approximate solution for t. It means that d2 th dx2 plus th minus x is not equals to 0. Okay, so with the approximate solution, our strong form is not satisfied. Because of that, the strong form, it is satisfied in a weighted integral sense with respect to the approximate solution. So th is the approximate solution and h represents the approximation. So we can perform the integration by parts for this expression, and we can do it like, so here omega is varying from 0 to 1. So it is w. So wx, we write it in short as w d2 th dx2 dx plus integration 0 to 1 wx th. Th is also a function of x dx minus integration 0 to 1 x wx dx equals to 0. Now we omit the term th. We write, for simplicity, we represent th by t, but we know that this t, this is approximate t. Okay, this t is approximate t. So we can write it as integration 0 to 1 w d2t dx2 dx plus integration 0 to 1 w2 wt dx equals to integration 0 to 1 x w dx. So the terms that contain both w and t, we keep them in the left side because they will give us the bilinear form, and the term that contain only the w and no other unknown, we keep them in the right hand side. So w is also a known quantity. Now, if we perform the integration by parts, first we get here w into integration 0 to 1 d2t dx2 dx minus integration 0 to 1 dw dx integration 0 to 1 d2t dx2 dx then dx plus integration 0 to 1 wt dx equals to integration 0 to 1 x w dx. Then we can simplify it as w into dt dx, which is going from 0 to 1, minus integration 0 to 1 dw dx dt dx dx plus integration 0 to 1 w2 dx equals to integration 0 to 1 xw dx. Now, this is the desired weak form for this particular strong form. If we look at this weak form, then we see that here the governing equation was of second order. So for this, we can maximum perform only one integration. We have performed one time integration. Now it has reduced the order of the equation. It has come to a first order equation with dt dx as the first order term. In this expression, the first term in the left hand side, this is the representing the natural boundary condition term. For the present problem, we do not have any natural boundary condition term, and because of this, we can discard this term, and remaining terms, the remaining second and third term in the left hand side, they will give us the bilinear term, and the right hand side they will give us the linear term. So we can simplify this as integration 0 to 1 dw dx dt dx dx minus integration 0 to 1 wt dx equals to minus integration 0 to 1 xw dx. Now, this left hand side portion, they construct this portion, it constructs the bilinear term wt, and the right hand side is it constructs the linear term lw. Now we can easily see that this, if we write this left hand side terms as bt comma w, then we see that our expression does not change. It means that if we interchange the positions, if we interchange the positions of w and t in this particular left hand side portion, then we see that this expression, it does not change. It means that bwt equals to btw. So from here we understand that the bilinear form which is have in the left hand side, that is symmetric also. So it means that in this case we are dealing with a self adjoint problem. So this is the bilinear form. The bilinear form is symmetric. So if the bilinear form is symmetric, then we have the quadratic functional capital IT, it exists. So we can say that for this case, for bilinear symmetric form, the quadratic functional capital IT, it exists. Now our form was, I just rewrite this equation as integration 0 to 1 dw dx dt dx minus integration 0 to 1 wt dx equals to minus integration 0 to 1 wx dx. Now this is our bw comma t, and this is our lw. So we know that the quadratic functional it equals to half of bt comma t minus l of t. So from here we can construct the quadratic functional. So capital I is the quadratic functional operator, So capital I is the quadratic functional operator, and I capital T, this is the argument here, it is temperature. So we can write it as half of integral 0 to 1. Now replace W by T, so we can get it as dt dx whole square minus, here W will be replaced by T square, so it is T square. So this is dt dx whole square minus T square dx, and then this half is outside. So this is half btt. So btt is integration 0 to 1 dt dx whole square minus T square dx, and then Lw we have to subtract from this. Lw is negative quantity, so it will be a plus term. So it will be integral 0 to 1. Now W will be replaced by T. So we have Tx dx. So we have our quadratic functional ready for performing the Rayleigh-Ridge approximation. Now let us construct the trial solution. So the trial solution for temperature, Tx equals to an n parameter expression is Cj phi jx plus phi 0. Here Cj, this is for n parameter. This Cj, these are the ridge coefficients. J varies from 1 to n, and phi jx, these are the approximate functions, the basis functions which we choose, and phi 0, it is selected in such a manner that Tx, it satisfies the boundary conditions, particularly the essential boundary conditions at left and right, both the boundaries. So for this problem, for simplification, let us take n equals to 1. So if we take n equals to 1, this is known as one parameter approximation. So one parameter approximation will be Tx equals to C1 into phi 1x plus phi 0. So in the previous class, we have shown that if x equals to 0 to 1, if x varies between 0 and 1, then we can choose the polynomial as phi jx equals to x to the power j into 1 minus x. This is just a possible choice. Using this, we can see here that the trial solution equals to C1 phi 1x will be x into 1 minus x plus phi 0. So our Tx is C1x minus C1x square plus phi 0. Now we have to check the boundary conditions. So at x equals to 0, Tx equals to phi 0. If we take x equals to 0, this term will be 0. Then Tx will be phi 0. And if we take x equals to 1, then also this term will be 0. So this is 0 for x equals to 0, and 1. So in both cases, Tx equals to phi 0. Now we have the homogeneous boundary condition at both the boundaries. So the only solution here for the Tx is that Tx equals to, so phi 0 has to be 0 to satisfy the essential boundary conditions. So Tx equals to C1x minus C1x square plus 0. So it means that phi 0 equals to 0. This is to satisfy the EBCs, to satisfy the essential boundary conditions. So finally, our trial solution is Tx equals to C1x minus C1x square. So this is the polynomial which we have to use, we have to substitute in the quadratic functional. So now here dt dx, from here we can calculate dt dx equals to C1 minus 2C1x. So when we substitute this, we find this half integration 0 to 1 C1 minus 2C1x whole square minus C1x minus C1x square whole square. Then this we perform the integration dx. Actually this we can write it directly with the third bracket. plus integration 0 to 1. Our temperature is C1x minus C1x square. So this is Tx. So it is C1x minus C1x square into x dx. So if we expand these terms, then we find that the functional it, it is half into integration 0 to 1 c1 square minus 4 c1 square x plus 4 c1 square x square minus c1 square x square plus 4 c1 square x cube minus c1 square x to the power 4 dx plus, if we perform the integration here, we are having here 0 to 1 c1 x square minus c1 x cube dx. In the next step, we get half of integration. Then if we perform the integration, this gives us, this is first one was c1 square minus 4 c1 square minus 4 c1 square x plus 4 c1 square x square minus, just I cross check once, c1 square x square plus 2 c1 square x cube. So this will be 2 c1 square x cube minus c1 square x to the power 4. So here, after integration, we are getting c1 square x minus 4 c1 square into x square by 2 plus, this will give us 3 c1 square x square. So 3 c1 square into x cube by 3 plus 2 c1 square into x to the power 4 by 4 minus c1 square into x to the power 5 by 5. So this is with the range 0 to 1. And if we perform integration for the second part, this portion, this is giving us c1 x cube by 3 minus c1 x to the power 4 by 4, where x is varying from 0 to 1. So here we substitute the range between 0 and 1. So it is c1 square minus 2 c1 square plus c1 square plus c1 square by 2 minus c1 square by 5 plus, this is c1 by 3 minus c1 by 4. So if we check it, c1 square and c1 square, so this portion, this is equals to 0, then we are left with half into 5 minus 2 plus 12. So it is c1. 4c1 minus 3c1. So it is c1. So from here we can get 3c1 square plus 20 plus c1 by 12. So finally, our quadratic functional is 3c1 square by 20 plus c1 by 12. So it equals to 3c1 square by 20 plus c1 by 12. Now, for minimization of the quadratic functional, we have only one coefficient. So this is a function of c1 only. So di dc1 equals to 0 for minimization of the quadratic functional. Di dc1 equals to 0. This gives us ddc1 of 3c1 square by 20 plus c1 by 12 equals to 0. So this will give us 6c1 by 20. Let us just check it. 6c1 by 20 plus 1 by 12. This gives us 6c1 by 20 plus 1 by 12. 1 by 12 equals to 0, then from here we find that 3c1 by 10 equals to minus 1 by 12, or c1 equals to minus 5 by 18. So our trial solution is tx equals to c1x into 1 minus x. So it is minus 5 by 18 x into 1 minus x, or it is 5x by 18 into x minus 1. So this is the closed form approximate solution of the given strong form by using the Rayleigh method. Now let us introduce the concept of the method of weighted residuals, or capital MWR. To do that, first let us introduce the concept of residual. Now, when we have a strong form, for example, let us consider the Poisson's equation again, k d2t dx2 plus q equals to 0. This is the strong form. This is the exact equation, or the continuum equation. This equation can be represented as LT plus F equals to 0, where L is an operator. L is an operator. So here L equals to d2 dx2, and F equals to q. So LT plus F equals to 0. This is the exact equation where the temperature, it exactly satisfies the Poisson equation. Now let us consider some approximate value of temperature that we denote by TH, the approximate value with which the operator equation is not satisfied. With approximate solution, TH, we get that L of TH plus F is not equals to 0. It means that with the approximate solution, the left hand side and the right hand side, they are different. Okay, so in the exact equation, left hand side and right hand side, they were same. That was represented by the equality symbol. And when we use the approximate solution, then the left hand side and right hand side, they are different, and because of that we have a difference, and this difference gives us a poorer solution. So we say that if this difference is minimized, we cannot make this difference 0. We can make the difference 0 only for the exact equation. So our objective is that we try to find out the solutions for temperature in such a manner that this difference can be minimized as much as possible. So this difference, which is a function of spatial coordinates, is known as the residual of that particular governing equation. So residual is denoted by the symbol capital R. This is a function of the coordinates. So residual equals to LHS, left hand side, minus RHS of the approximate equation. Okay, so here I mentioned that residual and error, they are not same things. Residual differs from error. In the residual, we talk about the difference between the left hand side and right hand side of the governing equation when we try to satisfy with respect to the approximate solution. So residual is related only with the governing equation, and when we talk about the error, we talk about the difference in the exact solution and approximate solution of a particular equation at a point or at many points or at the same point at different time levels or at different equation levels. So clearly I say that by residual we talk about the equations, and by error we talk about the solutions of that particular equation. So in that sense, the virtual displacement or the weight function, it is equivalent to the error of the solution. Okay, now our objective is that we propose a method in which we find the high quality solutions by minimizing the residual. Okay, so this residual, it is a function of coordinate. It means that it is present at every location. So we can define a residual vector. Now this can be represented as the residual vector, which I simply denote by the symbol capital R bar, and then at every point within a domain we can define the weight functions. When we talk about the variational methods, then we don't have any point within the domain. We take the whole domain at a time and we do not have any mesh generation. So we can talk about the residual vector and we can talk about the virtual displacement. So this is a problem on temperature. So the virtual displacement of temperature, this we can write it as delta T. Now this is the virtual displacement in temperature or weight function. This we already discussed, or test function. So weight function is also known as test function. So this delta T, we have n number of values. So delta T is a vector where delta is the variation. So delta T is a vector quantity. So here the residual acts as the force and delta T acts as the virtual displacement. So delta T dot R represents the virtual work. So for a vector capital R bar and the virtual displacement delta T bar, the work done is equals to 0. Then we say that R bar and delta T, they are orthogonal, or we can say that weight function and residual, they are orthogonal to each other, or there is no means work done by the residual force, it is equals to 0. Now when we operate this expression for the entire domain, this expression can be written as integration over omega w bar dot r bar d omega equals to 0, or we can write it as integration over omega w1 r1 plus w2 r2 plus wn rn d omega equals to 0, or we can even write it as integration over omega vector w and residual vector d omega equals to 0. So this is the method of weighted residual, where we write that in short it is MWR. By MWR we say that we find the integral form of the governing equation by taking the dot product of the residual vector and the weight function or the virtual displacement over the entire domain. Weight function we define such that the value of weight function, it changes from 0 to 1. So weight function can be a fraction. It is a known quantity. It varies between 0 and 1. And at Dirichlet nodes, at the essential boundary nodes, the value of weight function is 0. And for finite volume method, we have the weight function value equals to 1. So this is the foundation for the method of weighted residual, or MWR. In Rayleigh-Ridge method, we needed the adjoint self-adjoint operator. If it is not self-adjoint problem, we cannot use Rayleigh-Ridge method. But for the method of weighted residuals, there is no such restriction. Any kind of differential equation, be it linear, be it non-linear, be it solid mechanics, be it in fluid mechanics, be it in symmetric operated or with asymmetric operator, we can use the method of weighted residuals. Okay, so method of weighted residuals, already I told that there are 4 fundamental parts. One is the Galerkin or Bubnov-Galerkin method. Okay, so this is after the Russian mathematician B.G. Galerkin, who contributed largely in the finite element development. So this Galerkin's method is used for the solid mechanics problems, and for the thermofluids, it is used for the diffusion dominated problems or the heat conduction problems. We use the Galerkin formulation. When we use the Galerkin formulation in heat conduction problem, we deal with symmetric methods and we get symmetric matrix. So because of this, what is happening that the solutions for the Rayleigh-Ridge method and solutions for the Galerkin formulation, they match. But it does not mean that Rayleigh-Ridge and Galerkin are same. They are different methods. But we select the weight function and the approximate function from the same vector space, and because of that we get the same solution under prescribed essential boundary conditions. Okay, so it should be very clearly mentioned that Galerkin method is valid for any kind of problems. Okay, we don't use it for fluid mechanics though, for conventional fluid mechanics, but this Rayleigh-Ridge method is not universally applicable for all kinds of problems. For heat conduction problems, Galerkin formulation, it gives us the symmetric matrix, and this Galerkin formulation, it is equivalent to the central difference scheme used in finite difference or finite volume method. So the Galerkin formulation in variational methods or finite element methods, that is equivalent to central difference scheme used in finite difference or finite volume methods. So in Galerkin formulation, the weight function, this is a function of space. Weight function becomes approximate functions. It means that weight function and approximate functions, they are the same basis functions. The second method we can talk about the least squares method. So in least squares method, we find the integral form of the governing equations by minimizing the square of the residual. So when we write about the residual, this residual, it is a function of the left-hand side and the right-hand side of the governing equation. It means that residual is a function of the spatial coordinate and also of the unknown quantity. Now this unknown quantity, it is a function of space. We wrote it as the trial solution Cj phi jx plus phi 0. So j is varying from 1 to n for n parameter approximation. Now this tx, we can represent that tx is a function of this unknown coefficients cj. So this can be written as r of x comma cj. Now the least square method requires that the square of the residual on the domain omega, the residual r of x comma cj, so square of the residual over the domain d omega, it should be 0. So this condition, this gives us the weight functions for the least squares method. Now this we can simplify by using the Leibniz theorem. So use Leibniz theorem to perform this integration. So let us consider this is omega and these two boundaries, they are outside omega. We denote these boundaries as omega minimum and this boundary we denote as omega maximum. These are the fixed points. They are having fixed coordinates. So this we can write it as del del ci from omega minimum to omega maximum r of x comma cj whole square d omega equals to 0. This can be written as r of omega max comma cj into del del ci omega max minus r of omega min comma cj whole square, this is minus sign, into del del ci of omega min plus integration from omega min to omega max del del ci of r of x comma cj whole square d omega equals to 0. This is the condition. Now omega max and omega min, they are the fixed coordinates, and because of that these two derivatives, they are 0. So in the left hand side of this integration, we are getting that the first two terms, they are 0, and then we are left with integration of omega del del ci r of x comma cj whole square d omega equals to 0. This gives us 2 into integration over omega del r x comma cj del ci into r of x comma cj d omega equals to 0. So finally we get integration over omega del r x comma cj del ci r of x comma cj d omega equals to 0. Comparing this expression with the basic expression of integration of w r d omega equals to 0 over omega for the MWR statement, we understand that wx equals to del r x ci del ci. So we calculate the weight functions for the least squares method by using this expression, by using the derivative. So the coefficient matrices for least squares problems are always symmetric. So we have discussed the Galerkin or Bubnov-Galerkin formulation, then least squares method. Next one, we have the collocation method. So here, to define the weight function for the collocation method, we take the help from Dirac delta function, delta x. Dirac delta function the weight function wx, it can be represented as del of x minus xi. Okay, so this relationship we find out for finding the MWR format using the collocation method. Now we have integration over omega wx r of x comma cj d omega equals to 0, and then this wx equals to del of x minus xi, where xi represents a location of the collocation point. So xi is the location of collocation point, which is a constant collocation point. So xi, we just take it a point within the domain. So then from here we are getting r of x comma cj d omega equals to 0. Now this Dirac delta function, it has a property integration over omega del of x minus xi fx d omega equals to f of xi. So this property we use here, we use this property here, and from there we find that r of xi cj equals to 0. So this gives us the governing algebraic equation for finding the coefficient cj. This is becoming the algebraic equation at collocation point xi, collocation points xi to find cj. So this is the collocation method. And finally, we are left with the Petrov-Galerkin method. So this Petrov-Galerkin formulation, it is used only for the fluid mechanics problems, not in the solid mechanics problems. Only for fluid mechanics problems, fluid mechanics or convection dominated problems. Not used for heat conduction problems, heat conduction or self-adjoint problems. So in finite difference or finite volume, when we talk about the upwinding scheme, we talk about the Petrov-Galerkin formulation corresponding to the variational method or the finite element method. Okay, so when we talk about the Galerkin formulation, we don't talk about the directional dependence or directional bias, but when we talk about the Petrov-Galerkin formulation, we talk about the directional bias because of the fluid flow. So in Petrov-Galerkin formulation, the weight function, it is perturbed approximate function. So this is the original Galerkin approximate function. We perturb it by adding a perturbation term del phi I x. So this is the Petrov-Galerkin formulation that weight function and the approximate function, they do not come from the same vector space, or the basis for weight function and the approximate function, they are different. This perturbation term, this helps us to consider the direction of the fluid flow. Now we shall show all these four methods for a particular problem that we have already solved for the Rayleigh-Ridge problem. So our governing equation that we have already considered, the strong form is d2t dx2 plus t equals to x over 0, 1, t0 equals to 0 and t1 equals to 0. These are the homogeneous essential boundary conditions. So this constructs the strong form of the equation. We want to find the Galerkin formulation for this case. Now the Galerkin method, already I told you that W equals to phi Ix. This happens in the Galerkin formulation and the Rayleigh-Ridge formulation, and because of this, whatever solution we already obtained by using the Rayleigh-Ridge method, we are expecting to get exactly the same solution by using the Galerkin formulation, because we are using essential boundary conditions at both the boundaries and we are having the same approximate functions. So the trial solution, we shall consider this for one parameter. We shall solve this for one parameter. So J will be 1 and C will be only C1. So we shall deal with only a single constant. Okay. So this is Cj phi j x plus phi 0, and I just mention here that this Tx, the trial solution, this has to satisfy both essential and natural boundary conditions. This I emphasize. It has to satisfy essential boundary condition also, and it has to satisfy the natural boundary conditions also. For n equals to 1, our Tx equals to C1x, and we have already shown that phi 0 equals to 0 for this problem in order to satisfy the essential boundary conditions, and C1x equals to C1, this is C1 into phi 1x, C1 into phi 1x. So C1 into, this was C1 into x into 1 minus x. So this is our phi 1x. So it is C1x minus C1 x square. Now the MWR statement gives us, the MWR statement gives us integration over omega WR d omega equals to 0. This gives us integration from 0 to 1. Now W equals to phi 1x. So W equals to phi 1x, and from here we can find out dt dx. We have already Tx equals to C1x minus C1x square. So dt dx equals to C1 minus 2C1x, and d2t dx2 equals to minus 2C1. So our residual, it is d2th dx2 plus th minus x not equals to 0. So our residual is d2tx ds2. This is minus 2c1. th is c1x minus c1x square minus x. So this is the residual, minus 2c1 d2t dx2 minus 2c1 plus c1x minus c1x square minus x. X is the source term here. So here, this is the weight function for this Galerkin formulation weight function is the approximate function into the residual. So our residual is minus 2c1 plus c1x minus c1x square minus x dx equals to 0. Here we get integration 0 to 1. So this phi 1x is x minus x square. Phi 1x is x minus x square into minus 2c1 plus c1x minus c1x square minus x dx equals to 0. Now we just perform the multiplications, then we are getting minus 2c1x plus c1x square minus c1x cube minus x square. Then we are getting plus 2c1x square minus c1x cube minus c1x cube plus c1x to the power 4 plus x cube dx equals to 0. So we can simplify this expression as integration 0 to 1 minus 2c1x plus 3c1x square. c1x square is present for two times, minus 2c1x cube minus 2c1x cube plus c1 x to the power 4 minus x square plus x cube dx equals to 0. So this is the expression. I just check it once. Minus 2c1x plus 3c1x square minus 2c1x cube plus c1x to the power 4 minus x cube x square plus x cube dx equals to 0. After performing the integration, we get here minus 2c1 into x square by 2 plus 3c1 into x cube by 3 minus 2c1 into x to the power 4 by 4 plus c1 into x to the power 5 by 5 minus x cube by 3 plus x to the power 4 by 4 from 0 to 1 equals to 0. This gives us, here you are getting minus c1 plus c1, this is minus c1, this is plus c1 minus c1 by 2 plus c1 by 5 minus 1 by 3 plus 1 by 4 equals to 0. This gives us, these two parts they cancel out. So minus c1 by 2 plus c1 by 5 equals to 1/3 minus 1/4. So from here we are getting 10 minus 5c1 plus 2c1 equals to 12, 1 by 12. So from here minus 3c1 by 10 equals to 1 by 12, or c1 equals to minus 1 by 12 into 10 by 3 equals to minus 5 by 18. So our approximate solution is Tx equals to c1 into x minus x square. So we are getting here c1 is minus 5 by 18 x into 1 minus x. Okay, so we got the exactly same value by using the Rayleigh-Ridge method. Okay, so The Rayleigh method and Galerkin method, for certain cases, they provide us the same solution for the adjoint problems, self-adjoint problems. So this is the case of the Galerkin formulation. Now let us go for the collocation method. If we go for the collocation method, we need the collocation point xi within the domain. For this particular case, single degree of freedom case, we have this is x equals to 0 and this is x equals to 1. So we have to select only one point for a single term approximation. So for this case, the best point is the midpoint of the bar, which we take as xi equals to 0.5. So xi is the collocation point. So we have already shown that at the collocation point, the residual xi cj, it disappears. It means that here we have only one point. So the residual at x equals to 0.5, comma c1, we have only one coefficient for one term equals to 0, and residual, we have already shown it, that residual of the governing equation, this was, I have to just check it and I just write it, residual was minus 2c1 plus c1x, residual was minus 2c1 plus c1x minus c1x square minus c1x square minus x. I just cross check it once more. Minus 2c1 plus c1x minus c1x square minus x minus c1x square minus x. So here this residual, we just substitute this coordinate of x coordinate and then we find it. So here putting x1, this is the collocation point I equals to 1, x1 equals to 0.5 in R of x1 c1 equals to 0, we get from here minus 2c1 plus c1 into 0.5 minus c1 into 0.5 whole square minus 0.5 equals to 0. It means that we are getting here c1 into minus 2 plus c1 by 2 plus 1 by 2. Make a small correction here. Minus 1 by 4 equals to 0.5. So this algebraic equation will give us the value of this coefficient. So it is c1 equals c1 into minus 2 plus half minus 1/4 is 0.5. So from here we are getting c1 into, this is 4, so minus 8 plus 2 minus 1 equals to half. From here c1 equals to, here minus will come, minus half into 4 divided by 7. So c1 equals to minus 2 by 7. So using the collocation method, our solution is, approximate solution is tx equals to c1 phi1x minus 2 by 7 x into 1 minus x. Okay, so this is the collocation solution, and in Galerkin formulation we already got minus 2 by 7, it was minus 5 by 18. Okay, now we go for the least squares method. So in least squares method we have only one weight function, least squares method. So we have wi equals to del ci of r of x comma cj. This was the expression for finding the weight function. For us, we have only I equals to 1 and j equals to 1, both. So we have only one weight function. So this weight function for I equals to 1, we have only one weight function, w1 equals to del c1 of the residual r of x comma c1. Means here temperature R means we can write x also, no problem. X comma c1, then this is the R of x comma c1. If we take the derivative of this gives us del with respect to c1, it gives us minus 2 plus x, then it gives us minus x square. So the weight function is minus 2 plus x minus x square. Now the MWR statement, it gives us integration over omega WR d omega equals to 0. This gives us omega is from 0 to varying from 0 to 1. Weight function is minus 2 plus x minus x square, and the residual is minus 2c1 plus c1x minus c1x square minus x dx equals to 0. So if we perform this product and if we simplify, then we shall get our solution. Okay, so I can show some of the steps for this. Integration 0 to 1, then we are getting here 4c1 minus 2c1x plus 2c1x square plus 2x minus 2c1x plus c1x square minus c1x cube plus x square plus 2c1x square minus c1x cube plus c1x to the power 4 plus x cube dx equals to 0. Let us make a cross check here. So it is 4c1, then minus 2c1x plus 2c1x square plus 2x. Next it is minus 2c1x plus c1x square minus c1x cube minus x square. So there is an error in the sign, so this should be minus x square. Next we have plus 2c1x square minus c1x cube plus c1x to the power 4 and plus x cube. So the similar terms we can just take together, integration of 0 to 1. So it is 4c1. Now 2c1x and 2c1x, they are common. So we are getting minus 4c1x. Now c1x square, here is 2c1x square, c1x square, 2c1x square. So there is 5c1x square. Then c1x cube minus 2c1x cube. Then we are left with c1x to the power 4 plus c1x to the power 4. Then the algebraic terms are, remaining terms are 2x minus x square plus x cube dx equals to 0. Still I want to cross check it. 4c1 minus 4c1x, 2c1 square, c1 square 1. So 5c1x square minus 2c1x cube plus c1x to the power 4, then plus 2x minus x square plus x cube. Let us perform this simplification. Then we get from here, after performing the integration, 4c1x minus 4c1x square by 2 plus 5c1x cube by 3 minus 2c1x to the power 4 by 4 plus c1x to the power 5 by 5 plus 2 into x square by 2 minus x cube by 3 plus x to the power 4 by 4. From 0 to 1, this is 0. If we put the values, then by putting the values of x, we get here 4c1 minus 2c1 plus 5 by 3c1 minus c1 by 2 plus c1 by 5 plus, here it is 1 minus 1/3 plus it is 1/4 equals to 0. Then we just shift the terms in the left hand and right hand sides. If we do that, from here we get C1. These two terms, they give us 2C1. So 2 plus 5/3 minus half plus 1/5 equals to minus 1 plus 1/3 minus 1/4. So this calculation I do here. Space is not there here, so I do this calculation here. In this portion, I just do this calculation. The remaining part I shall show it here. So here it is C1 into 60. So this is 120 plus 100 minus 30 plus 12 equals to minus 1 plus 1/12. So this is giving us minus 11/12. And in the left hand side we are getting C1 into, at the bottom it is 60. This is 220, 232 minus 30. 232 minus 30 means 202 equals to minus 11/12. This gives us C1 equals to minus 11/12 into 60/202. So it is, what I understand, this gives us C1 equals to minus 55/202. So for the least squares method, Tx equals to C1x into 1 minus x equals to minus 55x/202 into 1 minus x. And finally, we are left with the PG method, the Petrov-Galerkin method. So our weight function, here we choose it like weight function equals to phi1x plus perturbation of phi1x. Phi1x we have already taken as x into 1 minus x. So it is x minus x square. To make the term simple, just to make the term simple without any mathematical things or without any stability, nothing, we are just showing it for illustration, for explaining. Just because of that, just to make the calculation simple, we are taking the perturbation as positive x square. This we are taking as delta phi1x, so that we get a simple term to make the calculation simple, nothing else. Okay. Then if we use the statement of MWR, it gives us integration of 0 to 1 Wx Wr d omega equals to 0. We get from 0 to 1. Wx is x, and the residual, I have to check the expression for the residual once more. It was minus 2c1 plus c1x, minus 2c1 plus c1x minus c1x square minus x, minus c1x square minus x dx equals to 0. This gives us integration of 0 to 1 minus 2c1x plus c1x square minus c1x cube minus x square dx equals to 0. We perform the integration here. It gives us minus 2c1 into x square by 2 plus c1 into x cubed by 3 minus c1 into x to the power 4 by 4 minus x cubed by 3 from 0 to 1 is 0. From here you are getting minus, so 2 cancels, it gives us minus c1 plus c1 by 3 minus c1 by 4 minus 1/3 equals to 0. This gives us c1 into minus 1 plus 1/3 minus 1/4 equals to 1/3. This gives c1 into 12. Here it is minus 12 plus 4 minus 3 equals to 1 by 3. This gives c1 equals to minus 1 by 3 into 12 by 11. So it gives us minus 4 by 11. So for the PG method, our approximate solution is Tx equals to C1x into 1 minus x. C1 is minus 4 by 11 x into 1 minus x. So we have the solution from the Rayleigh-Ridge method and the remaining 4 MWR methods, and we got different solutions. So here we can summarize the solutions. So for Rayleigh-Ridge and Galerkin, we got, it was minus 5 by 18. So for Rayleigh-Ridge and Galerkin, our Tx was minus 5 by 18, 5x into 1 minus x. Then using collocation, we had Tx equals to, let us check the number what I got, minus 2 by 7, minus 2x by 7, 1 minus x. Then least squares, Tx value is minus 55x by 202 into 1 minus x. And finally we did this PG method, Petrov-Galerkin. Tx equals to minus 4x by 11 into 1 minus x. Let us cross check this PG solution once more. So it is x into minus 2c1 minus 2c1x plus c1 x square minus c1 x cube minus x square dx. So minus 2c1 into x square by 2 plus c1 x cube by 3 minus c1 x to the power 4 by 4 minus x cube by 3. So 2 cancel, they cancel out. We are left with minus c1, x is 1, 1/3, 1/3, this will give us 1/4. And this will give us 1/3 with minus sign. So this comes right side 1/3. Then we are left with C1 minus 1 plus 1/3 minus 1/4. So this gives us minus 12 plus 4 minus 3. So it is minus 15 plus 4 is minus 11 and 12. So it is 11, minus sign comes here 1/3. So it is minus 4 by 11. So these are the solutions for a single degree of freedom problem, heat conduction problem in one dimension by using one parameter variational methods. So let us just summarize this solution here. Now let us discuss the development of finite element method from the basic variational methods. The basic variational methods, they assume a profile assumption of the degree of freedom in terms of the trial solution. So in the trial solution, when we consider the phi1, phi2, etc., I mean the approximate functions, we actually assume the profile of the unknown quantity or degree of freedom within the domain. So the basic variational methods are not discretization technique, This is a fundamental difference with the finite element method. The finite element method is a discretization technique which is an improved variational technique. I mean that in finite element method, we discretize the domain or we split the domain into multiple non-overlapping finite elements, and then we implement the basic variational method for each finite element. So when we talk about the variational method, we talk about the continuum equation. But when we go for the finite element method, we finally deal with the algebraic equation and we don't get a closed form approximate solution. We get discrete solutions at discrete nodal points within the domain. So this is a fundamental improvement with respect to the variational method in case of finite element technique. So there are two major improvements in case of finite element method. In finite element method, in FEM, we generate mesh or grid. The mesh is composed of finite number of non-overlapping finite elements of known geometric shapes in general. This is the first part. When we generate the mesh, the approximate functions phi of variational methods are replaced by shape or basis functions psi function of space. I am writing in terms of one dimension that are systematically obtained using interpolation theory. In FEM, the degree of freedom or degree of freedoms is considered to vary as piecewise or element-wise continuous functions within the domain. So, for a given problem, if we consider this is the domain omega and we have a governing equation given in this domain, when we go for the variational method, we use the full domain, but in case of finite element method, we split the domain into finite number of elements, then we say that those are the finite elements. So in this right hand side picture, we are showing the case of FEM. The left hand side, we are showing the case of variational method where we use the full domain. In FEM, we split the domain. The domain is composed of finite number of subdomains that we denote as finite elements. So this particular segment, this is a finite element of mesh size or grid size delta x. This finite element we denote by its domain by omega e. Now, over the finite elements, the degree of freedom, if we consider the temperature is the degree of freedom. Now, for this finite element, this is the eth finite element. Here we have two nodal points. These are the nodal points. These circles are known as the nodal points. So these 2 points, we can identify them with local nodes 1 and 2. There are two nodal points per element. So here we can consider that we have temperatures T1E and T2E at the boundaries of the nodal points. Now, within this domain, let us consider the true variation of the temperature is like an unknown curve. This is the true variation of the temperature which we substitute or which we assume to be a piecewise continuous function. So the above curve, this is the actual profile of DOF, and this below curve, this is the assumed profile of DOF. Now, this assumed profile of DOF, this is based on the interpolation function. So in this case, we are showing the assumed profile to be a straight line. It means that within this element E, there are two interpolation functions, one for node 1 and one for node 2. Both of them are linear functions. Because of that, this assumed variation, this is a linear combination of those two interpolation functions, and then the linear combination is also a straight line. The word piecewise continuous function, it implies that when we go for the next element, we have the profile here. So at the junction of two successive elements E and E plus 1, and this, we are having the same value of temperature or the same value of the degree of freedom. So at the junction, same value of DOF or continuity of the primary variable or primitive variable or the DOF. So the major improvements of the variational method to finite element method is that in finite element method, we discretize the domain, and when we discretize the domain, we actually split the domain into multiple number or into finite number of non-overlapping subdomains that we identify as finite elements. Those finite elements cannot be of infinitesimally small size. They should be of perceptible dimensions. And then we integrate the governing equation, which are now not valid into any point within the domain. It is valid only at the selected points in the domain. So in the continuum sense, when we are dealing with the exact equation or the continuum equation, then the governing equation, it is valid at any location at any 2 points that are separated by a distance of infinitesimally small value. But when we go for the finite element, finite difference or finite volume kinds of methods, then we introduce finite distances between these points, so that distance between two successive points or distance between the neighboring points, they cannot be infinitesimally small. It means that now that we are moving from the continuum approach to finiteness. So the solutions which we calculate by using the numerical techniques like finite element kinds of techniques, we actually solve the unknown quantities at selected points. Then the continuum equation now replaced by a large number of algebraic equations, and that large number means it is a finite number, and because of that we say that we perform discretization. We solve the equation at discrete points. Those points are generated during generation of mesh. Okay, so now we make the differences between the variational method and the finite element method. So this is variational method, this is FEM. So variational method is not a discretization technique. It is not a discretization technique. FEM is a discretization technique. So discretization is the process of converting a continuum differential equation or system of continuum differential equations to linear or linearized algebraic equations. Okay, so in this process we discretize the governing equation, we discretize the initial conditions, we discretize the boundary conditions, and before all this, we discretize the domain or we generate the mesh. The second point is that the variational method, these are the initial methods for integral approaches from strong form. So the variational methods are the initial approaches of integrating the governing equation, and finite element method is the implementation of variational methods to all the elements in the mesh, in the FEM mesh. Thirdly, we can write that the approximate functions phis are not obtained systematically and accuracy is poor. In finite element method, the phis, the approximate functions, are replaced by shape function size. So size are obtained systematically. Accuracy is very high. Accuracy of the solutions then point 4 we can write that we get problems while dealing with complex geometries in multi-dimensions using the variational methods, and finite element method is highly flexible and it works very effectively in case of complex geometry in multi-dimensions. A fourth point we can write that variational method gives closed form approximate solutions. In finite element method we get highly accurate solutions at discrete nodes. So I emphasize here that the finite element method, it has been developed from the basic variational methods, or the basic variational methods, they are the foundations of the finite element method. So I briefly outline the finite element methodology here. So the first step is that given the strong form, the second step is that note the order of the strong form, perform integrations by half the order of the strong form. So this step gives us the weak or variational form of the given strong form. This weak form, it is for the entire domain. Now we have to implement the discretization technique. First we do the domain discretization. That is the fourth step, domain discretization. Or mesh generation. When you generate the mesh, then that time we construct certain arrays. Okay. So along with this, with the aid of IEN or connectivity array. Next step is identify the boundary nodes and generate local and global equation number arrays. Thus, from here, the sixth step is derive the element level matrix and vector equations for an arbitrary element. In the seventh step, implement the boundary conditions so update the right hand side element level load vector, load or force vector, and augment load vector FE and augment the element level stiffness matrix KE if required based on the boundary conditions. In the eighth stage, perform assembly of the element level matrices and vectors using the LM array. LM array is known as the location matrix, which we shall discuss in the next week. And the final step is solve the global matrix equation system KT equals to F and then post process. So in a nutshell, this flow chart, it shows the FEM steps starting from the strong form. Here, the main difference from the variational methods is that we create finite elements and then we implement the variational methods per finite element such that at the junction of finite elements, when we have common nodes, the primary variable such as temperature, velocity, pressure, etc., they must be continuous or they will have the same value so that we have a piecewise continuous distribution of the degree of freedom. During the process of mesh generation, we choose the element type. If it is in one dimension, then we use the bar elements. And if it is in two dimensions, then we go for the triangular elements or the quadrilateral elements. So during mesh generation, we select the element type and also select the interpolation functions for the degree of freedom. Okay, so if it is a thermofluid problems, we use interpolation functions for the spatial coordinates and interpolation functions for the degrees of freedom which are of the same order. So such formulations are known as isoparametric formulations. So profile assumption or how the degree of freedom changes within the element length. It is an important choice which we have to make along with the mesh generation. So here I make some more information regarding the matrix structure Kt equals to F. So the matrix equation system for steady state problems, it is converted to Kt equals to F format. Now in solid mechanics, the law of elasticity, Hooke's law, is given by F equals to minus Kx. So F is known as the load or force vector. This K is the stiffness matrix and X is the displacement. K is the stiffness matrix and X is the displacement. Now, since FEM was developed in solid mechanics, the same terminology we just continue for this matrix equation system where this assembled global matrix equation, even at the element level, it is known as the stiffness matrix. Capital T, this is the displacement or degree of freedom or the unknown, and small f, this is the force or load vector. This Kt equals to F is a special case of a more generalized ordinary differential equation. That ordinary differential equation, we can write it as mt double dot plus m tilde t dot plus Kt equals to F. This is an ordinary differential equation or ODE in time where T double dot, it means d2t dt2 and T dot means dt dt. This kind of form is known as semi-discrete form of the strong form. So here, if we look at the semi-discrete form, this form is very much similar to the form which we use for the vibration problems. The equation of motion of a rigid body mx double dot plus cx dot plus kx equals to F, which is written for a particle. Now here, this m and m tilde, in this case, they are known as the mass matrices. K is the stiffness matrix and F is the load vector. So more details on this will be provided during the discussion of transient problems. So this mt double dot term, it comes from the double derivative of time, and m tilde t dot term, it comes from the first derivative in time. Here I conclude today's lecture. In today's lecture, we have seen examples for heat transfer problems by approximate closed form solutions. We have used Rayleigh-Ridge method, Rayleigh-Ridge method. Then we have used the method of weighted residuals. Method of weighted residual. Using these two methods, we have obtained closed form approximate solutions. For the boundary value problem on the elliptic partial differential equation, in one dimension, subject to essential boundary conditions. We noted that the Rayleigh-Ridge and Galerkin solutions overlap for 1D boundary value problem using essential boundary conditions, essential or geometric or kinematic boundary conditions. We conventionally tell them as Dirichlet boundary conditions. And eventually, we have shown the development of finite element method finite element method development from the basic variational methods. So, basic variational methods are the foundations for understanding the finite element methods. Okay. So, for today's lecture, the textbook by J.N. Reddy, An Introduction to Finite Element Method. Thank you very much for attending this session.